Hello, my name is Reina Abhyankar, and I'm excited to present Intercept, our work on efficiently serving augmented large language models. Traditional LLMs perform solely text-based generation. However, recently there's been a trend of augmenting LLMs so they can interact with external entities. These range from tools like a calculator, calendar, or Wikipedia search to other models like text-to-speech or image generation. LLMs can also act as an embodied agent, navigating a virtual environment, or even a controller in a physical environment. And finally, the most popular current usage as a chatbot, back and forth with a human in the loop. The workflow of LLMs with interceptions is as follows. First, the LLM generates tokens that trigger a particular tool, environment, or another model, i.e. an augmentation. Then the serving system waits for a response while the query is dispatched to the augmentation. And finally, when the augmentation returns a response, the serving system appends a response to the sequence generated so far and continues normal generation. We studied the behavior of 6 different augmentations, which were described earlier, and we find that some tools like calculators are very fast, returning in less than 1 second. Other models like text-to-speech and Stable Diffusion can take 20 times longer, and a given user's request can be intercepted frequently, depending on the type of augmentation, ranging on average from 3 times to over 25 times. The next generation augmented LLM systems should account for all of these possibilities. Today's systems treat LLM interceptions as request completion. All context, i.e. each token's KV cache, is discarded. Then the KV cache for requests has to be recomputed when the interception finishes. We find that 37% of end-to-end request latency is spent on recomputation, while 27% of GPU memory is wasted. We call this strategy discard. When a request is intercepted, its memory is cleared. And then to recompute the request, the model has to prefill all of its KV, which can take 5 times longer than a typical decoding forward pass. The second strategy preserves the KV cache in GPU memory and waits for the interception to finish, at which point it can resume immediately without any recomputation. However, memory is unusable for other requests for the duration of the interception. The third strategy is to swap the KV cache out to CPU memory, i.e. offloading. When the request is being swapped out, the model waits. Once the request is fully swapped, can generation continue. Additionally, the cache must be swapped in when the interception finishes. Each strategy has different trade-offs. Recomputing and swapping both stall running a request in different ways, while preserving a request occupies memory. Our goal is to determine the best strategy for a given request, which is why we built InferCept. Our system has 3 main components. First, we quantify GPU memory waste per strategy. Second, we improve existing techniques. And third, we schedule requests to minimize GPU memory waste. InferCept sustains a 1.6 to 2 times higher serving load, completing twice as many requests compared to state-of-art systems. First, we unify each strategy under a single framework. Waste equals unused memory multiplied by time. For an intercepted request, we compute the system waste as a result of each possible decision, and then select the least wasteful option. Second, we improve individual strategies. For discard, we chunk the context into multiple segments and recompute 1 at a time per iteration. This minimizes stalling for running requests. For swapping, we overlap all data communication with computation. By profiling the model and the CPU-GPU bus bandwidth, we identify a swap token budget that can be swapped without incurring extra latency. This eliminates all waste from swapping within a certain limit. And finally, for scheduling, we sort all intercepted requests in descending order based on their memory waste, which we compute as a minimum of waste discard and waste preserve. We swap out the cache from these requests according to this order until we run out of the swap token budget. For the remaining pause requests, we discard their cache if its waste discard is smaller, and vice versa for preserve, then moving the requests to their appropriate queue. We compare against 4 baselines. First, VLLM, which is a state-of-art serving system, which treats interceptions the same as completion and defaults to round-robin scheduling. Second is improved discard, which discards token states but keeps the original arrival time, i.e. first come, first serve. Third is preserve, which keeps all cache in memory. And fourth is swap, offloading all cache to CPU memory. For our evaluation, we composed a dataset of the 6 augmentations we studied. Our results show that InferCept supports 1.6 to 2 times higher request arrival rates than VLLM at the same low latency, or even lower, with 1.9 to 12 times improved lower normalized latency, which represents time per output token. And our results hold as the number of devices increases proportional to model size, which is critical for scaling augmented LLM serving. In conclusion, InferCept is key to scaling the capabilities of LLMs beyond just text generation. LLMs will soon interact with private data, custom APIs, and physical environments, which are impossible to train for. Under this premise, any interaction outside the model is an interception. Eventually, we foresee LLMs will be augmented by default and will interact with each other as well as other modalities in compound AI systems. You can get InferCept by scanning the QR code, and you can read our full paper at the link in the description below. Thank you.